All right, I think we can get started. My name is Jason Masterakos. I am the head of the channel. The channel is called S.T.E.M Online Academy. For those of you who already are subscribers or viewers or whatever. What is the channel about, and how do we conduct things on the channel? So, the channel is mainly about mathematics and advanced physics education. Okay, so what we do, right, is we try to help, or you can say guide, or invigorate people's curiosity in these subjects, right, by looking at interesting concepts or advanced or problem solving questions. Okay, so mainly we're going to be looking at well, if you watch my last couple of videos, um, it's all been math based, but we also, as I said, we do physics based problem solving as well. Okay, so the last what we're looking at, right? What we're going to be looking at when it comes to these things is mainly concepts. Okay, so that's what I want to talk to you about. That's what we do as S.T.E.M Online, is that we talk about how to solve things as opposed to just using some mnemonic or formulaic approach. Okay, and my approach to solving problems has always been this. It's been the most effective for me. I hope it's going to be effective for you. That's the point of the channel, is to make uh, math and science more relatable and more interesting. Okay, so my three-pillar approach has always been: number one, make sure you understand the problem per se. Okay. So what I mean by that, whether it is an equation or it's a word problem or any of that, okay, you want to make sure that you understand what is being asked. Okay, because you want to be able to transpose or translate that to the next step, which is a model, right? Either a geometric or graphical model of the phenomenon or equation. Okay, so that's the because by doing that, you'll be able to make sense when you're doing your calculations or proofs. Okay, so once you have the model, right, this is a visual spatial approach. Once you have your graph or model, wherever it is, you can take that model, and then after based on what it's saying, you can say, oh, this makes sense or this doesn't make sense when I'm doing my next step, right? When I have to actually calculate something, maybe it's an area or volume or whatever it is geometrically, right? You can make sense out of it just by looking at the model. Okay, and then from the model, you should be able to go to step three, which is a mathematical interpretation or equation. And that's the easy part, because once you have the equation, you can apply a method to the equation. The hard part is step one and step two. Okay. But that's what this channel is about, is to increase your mathematical intuition, right? Because step one and step two are the intuition part. Step three is just the method part. Okay. The method part is the easiest part. Step one and step two is by far the hardest. Okay. So this channel is not just any mathematical channel, it's a math dojo. So what that means is we're going to get into some very interesting stuff right away. Okay, so let me pull up some stuff. Okay, for those of you who have been watching, as I said, you probably have noticed that S.T.E.M Online, the last couple of episodes, I've been doing a review of my book. I have a book out called Advanced Integration Techniques. Okay, and it's all about applied mathematics uh, and looking at like the applications, right? Methods and open-ended problems. So whether you're a student who wants to advance your integration techniques, you already know integral calculus or whatever, and you want to move further in it, you can check. This book will be for you, especially if you want to use it in later classes, right? In your calculus classes or complex analysis classes or numerical analysis. Or if you're looking for something that has to do with applications and you need to apply it in your engineering or physics classes. So this would be the perfect book for you. Okay, so let's get right to it. The first thing we're going to look at, so let me just open the board here. All right, so let's go to the entire screen. Okay, just give me a moment. All right. So what I want to bring up here, right, is, so here's where we're at, okay? So we're going to talk about the gamma function, okay? I'm going to explain it graphically, all right? So this is a problem from my book, all right? This is how the cover of my book, okay? All right, and we're going to be looking at specifically some properties of the gamma function, okay? Mainly in a geometric fashion. We'll get to the other stuff like solving equations and stuff like that, but we're going to look at the geometric uh, part of the gamma function. Okay, so let's go to the web here. Okay, and you would have already noticed. So here's what I have. Okay, we're going to look at a simulation. That's the point of this. Okay, we're going to look at a simulation because a simulation will give us a more of a interesting model of how the gamma function is plotted. Okay, so here's the gamma function first off, all right? And what you can see in the simulation first off, before I get to the graph here that has been modeled, is that there is some parameters in place of the model, okay? So we have something interesting here. So we have the x-axis, y-axis, the resolution, okay? Now, I can control these parameters and the x and y axis and chains and vary things as I want, right? Depending on what we're exactly looking at, okay? So if we go back here, okay, you'll notice that in this animation, okay, that this part here anyways, okay, on the right-hand side here, the curve that I'm modeling, all right, already has, you can see that it's not exactly, it's not asymptotic. The right-hand part is not asymptotic for the gamma function. Okay, so you see it looks almost parabolic, okay? Starts up and then goes down and then goes up again, okay? You'll notice that the gamma function, okay, is a little bit different than your regular function. It's not an x-y axis, it's a real. So there's a real part and an imaginary part to the gamma function, okay? So the real part, okay, is a real function of z. That means the real numbers, right? Minus 1, 2, 3, 4, 5, minus infinity, minus 6, 7. Doesn't matter what it is. They're not dependent on complex numbers. The imaginary part is dependent on complex numbers. So yes, there is a connection between the gamma function and real and complex numbers, okay? So anyways, we have this parabolic curve here. Almost, it's not exactly parabolic, it's almost parabolic. Now on the left-hand side of the quadrants here, you'll notice that we have something interesting, right? Well, if you look at the poles, okay, there's supposed to be poles here. There's a pole at 0. What I mean by pole is that there's something there that's behaving in an asymptotic way, okay? So there's a pole at 0, okay? There's a pole at 1. So you can see here, yes, there are asymptotes at -1, okay? So asymptotes at -1 here, okay? I wasn't able to plot the poles exactly, but they're highlighted in red, okay? Pole at -1, pole at -2, pole at -3, pole at -4, and pole at -5. So you can see that these curves are just approaching the asymptotes, okay? They're approaching the asymptotes. That's what an asymptote is, right? You only approach the dotted line, but you never hit it, okay? All right. So if you notice that, we're having asymptotes all over here, okay? Now, let's go and look down here. What else do we have, okay? So there's some more information on the model. The model that I have, the simulation I have, has also given us some very interesting features, special values, applications, fundamental properties, and even a historical background of where the gamma function first originated, okay? Now, if you look at the input, okay, if you look at the input of z, okay, z is equal to 1.14 plus 0.535 I. What does that mean? Okay, what does that mean exactly? So that's just a complex number, first off, right? for those of you who know your complex numbers, right? Z is always in the form of a plus ib. A is a real number, b is a complex number. So that 1.14, when z is equal to a is equal to 1.14, the real part, that is just past our gamma of 1 value, right? When gamma of 1, that dot on our curve here, gamma of 1 is equal to 1. So at 1.14, okay, that's just a bit past there, okay? So somewhere over there, if you were to look at it, it depends where we have our where we're putting our cursor. Okay, the input of z will change depending on where I put my cursor on the model, if that makes sense. As you can see here, it's not fixed, right? It's varying, it's changing. Okay. All right, so that's our input, right? It can change depending where I'm putting my cursor. Gamma of z, right? The argument gamma of z. Those things are okay. They're a little bit boring, but let's get into now this is the interesting stuff. This is what I find interesting, okay, is the properties. And I hope you'll find it interesting too, all right? So the properties, if you look at the properties in specific detail, there are some fundamental properties, okay? And I'm going to go through these properties later on in the live stream, okay? So in the live stream, okay, yes, we're going to talk about the fundamental properties. The first one is something called a recurrence relationship, okay? So what is a recurrence relationship when it comes to the gamma function, okay? So recurrence relationship, it just states that the gamma of the z plus 1 is equal to z times gamma of z, okay? Now, for those of you who know the gamma function, there's going to be two groups. There's going to be groups of you who know what a gamma function is and those of you who don't, right? So in this live stream, I'll discuss in detail what the gamma function is and more like what it is mathematically, and etc. Right now, I'm just explaining it graphically with a diagram, okay? So the gamma function, there's multiple relations. Gamma of z plus 1 is equal to z times gamma of z. Another one is a factorial relationship. For those of you know what a factorial is, and factorial is equal to n by n minus 1 times n minus 2 times n minus r plus 1, where r can be any value greater than 1, right? Okay, so because when you have a gamma, the gamma function has to do with n factorial, right? Your factorial is always decreasing. So for instance, if you had 3 factorial, it will be 3 by 2 by 1, which would be 6. Okay, if you had 2 factorial, it would be 2 by 1, which is 2. 1 factorial is 1. Okay, you always take the multiplicity product, right, of your number, right, then multiply it again minus 1, then multiply it again by the preceding term by minus 1 again. Okay, so that's what a factorial is, right? You should know what a factorial is, right? And then we have something called the reflection relationship. I won't talk about that in this video as much. We may look at it at some point. It's not the most important thing here, okay? We also have the duplication formula for the gamma function, not as important. It listed all of the important things. The main important things I want to talk about is the reoccurrence relationship and the factorial, okay? All right. Now, let's skip over some of these because I'll come back to this. Some historical context on the gamma function. So the gamma function, right, was introduced by Leonhard Euler, right? Leonhard Euler is a mathematician in 1729. The generalization of factorials, that's what he did. And he later studied, it was later studied, the gamma function, okay, by other mathematicians like Legendre and Gauss. Gauss is a very big mathematician as well. So they were very much interested in the gamma function. It has a lot of applications. We'll talk about the applications as well in this video. Okay. All right, so I want to give you a geometric thing here, okay, but let's get right back into it, okay? So we've talked about the gamma function, and one of the things I want to talk about, which was on on our simulation there is, well, what is the gamma function mathematically? The gamma function is defined as this. Let me just highlight this if I can. What color am I on here? Just 1 second. This guy right here. Gamma of some function of n, doesn't matter what I call it, okay, is equal to the improper integral of x to the n minus 1 times e to the negative x dx. Okay? So we want to use this function. That's what a gamma function is. Okay? And we're going to use some properties. We're going to prove that the gamma, right, the gamma of n plus 1 is equal to n, the gamma of n. Okay? That's what we're going to do. We're going to prove that using the gamma function. Now, since this is a live stream, I don't want to do all the talking, okay? Yes, I am a mathematician. This comes to me very, like, spontaneous. I can do this very easily, right? Yes, so for me, it's nothing. But my point is, I want to help you guys not only be interested in higher level mathematics, but to develop a strong mathematical intuition and to utilize your, your critical thinking skills, visual spatial skills, and creativity. And the best way to do that is by modeling and by interacting with the audience. Okay, I always believe that interacting with the audience is very important. Okay, so that's what I'm going to do. I'm going to try to engage you guys. Okay, so I want some chat participation. Okay, so that's what we're going to do. All right, so for any of you in here, right, if you want to prove that gamma of n plus 1 is equal to n gamma of n, right, for this proof, okay, I'm going to need you to guide me through it a little bit. I'll give you a hint, okay? Obviously, we need to, if we're looking for gamma of n plus 1 is equal to n of gamma of n, okay, we need to obviously start off by the definition of the gamma function, which we know above here. Gamma of n is equal to the improper integral of x to the n minus 1 of e to the negative x dx, okay? All right, so we have that. Now, so that's what we're going to use down here. Now we want to replace n for n plus 1. So what do you think? Anybody in the chat? Let me just take a look here. Okay, so I'm stop sharing temporarily, if possible. Okay, just give me a moment. Let's go to the desktop. Anyone? Oh, yes. Someone is. Yes. Let's see if anyone's in the chat that wants to communicate. You interested? Okay, so I'm seeing just one person wants to know what we're talking about. You interested? Okay, so in the meantime, I can't wait for one person. I'll continue going on, right? And if anyone pops in, we'll take it from there. But if not, we'll just proceed, I think. Yeah, so share screen. Okay, so let's go back. Okay, let's go back here. And okay, so we're back on the whiteboard. All right, so I was talking about showing how to prove gamma of n plus 1 is equal to n gamma of n. All right, so we're going to take n plus 1. For every n, replace it with n plus 1. So we get an improper integral, right, of x to the n plus 1 power minus 1 times e to the negative x dx. Why? Because we're looking for gamma of n plus 1, not gamma of n. So every n has to be replaced with n plus 1. Okay? The 1 and 1 cancels. I'm left with gamma of n plus 1 is the improper integral of x to the n times e to the negative x dx. Okay? Now, from here, what we're going to look at is we need to be able to integrate that guy. Okay, we need to be able to integrate x to the n times e to the negative x dx. All right, so the way to do that, right, for those of you who are in, who are in or have taken integral calculus, okay, that's another thing too. To understand a lot of my concepts from this book specifically, it's good if you know have a strong foundation, a pretty strong foundation in integral calculus and linear algebra, right? Some measure theory would be handy, but you don't need to know measure theory per se. But if you know measure theory in this book, you'll be very well prepared. Okay, but it's not required to have measure theory, but if you know it, it will be really handy. The reason why I'm bringing this up now is because that's the only way you're going to understand me is if you know these topics. Okay, and then you're going to learn newer methods based on the topics you know from before. Okay, so for those of you who have taken integral calculus, you should be able to know how to integrate this. Okay, so the way to do that, okay, for those of you in the chat or anyone who's watching, help me figure out how we do this. How are we going to integrate x to the n times e to the negative x dx? Any thoughts at all? Okay, so no thoughts at the moment, not in the chat. Well, integration by parts. Come on, guys. You have to use integration by parts because of the fact that this integral, right, is in the form of the integral of u dv. Okay, so what that means is that I am pretty much I can choose my u or dv. I have to choose my correct u and my correct dv in order to integrate properly. Okay, all right, so that's how we're going to be able to solve this. Other integral methods aren't going to work. U substitution, power rule, it wouldn't make any sense. This is not written in any of those mathematical forms. Okay, so we have to use integration by parts. Okay. All right, so looking at that, we're going to choose u equal to x to the n. Now my differential du has to be n times x to the n minus 1 times dx because it's a derivative. My dv, okay, my dv would be e to the negative x dx, because if my u is x to the n, the dv has to be e to the negative x dx. Now my antiderivative of dv has to be minus e to the negative x, right? Okay, very straightforward. Right? I'm not doing anything brilliant here. It's just some basic integration, okay? Now, you may be asking, how do we know how to choose our u or dv? For those of you who have already taken or in integral calculus, you should notice that, and know actually, that your u, okay, your u has to be chosen such that, your u and dv has to be chosen such that when you do integration by parts, your next line, right, because integration by parts is uv minus integral v du, your integral v du has to be simpler than this integral. to integrate. In other words, it has to be able to be integrated on the next step. Now, sometimes they're more complicated and may trick you. There may be multiple steps, but it should start to become easier. Okay, if not, you may have a problem. You may need to look back. If it's getting more complicated, look back and redo it. Choose your correct U and dV. All right. Now we have our next line of attack. Gamma of n plus 1. Gamma of n plus 1 will be the limit as t approaches infinity. Now, where is this t coming? Where is this limit of t approaching infinity come from? Well, remember, our gamma function, if you pay attention, is an improper integral. You should know improper integrals. Improper integrals mean that they're, well, not all of them. It's just, singularities or whatever, but when they're bounded, going from having infinities, right? When they have infinities involved, you need to be able, right, to put a limit as t approaches infinity. Okay, replace t's for your infinity or any variables, no matter what you call it. Okay, so take the limit as t approaches infinity of the entire bracket here. Okay, so then it's going to be, okay, right? So limit as t approaches infinity, all square brackets, minus x to the n e to the negative x from 0 to t. Okay, all right. How am I getting this? Is this u times v? Remember, it's u. I have to use a different color. My mistake. Sometimes things on live shows become awkward. Happens to all of us. Yeah. So u is x to the n, and v is minus e to the x. So u times v is minus x to the n e to negative x. Limits integration from 0 to t, right? And plus t to infinity. Minus the integral, right? Because it's integral v du. Integral from 0 to t. V minus e to the negative x du. And by x to the n minus 1 times dx. I hope that is clear. Okay. All right, so we have that. On the next step, we have the limit as t approaches infinity of x to the n e to negative x 0 to t plus n times the integral from 0 to t of x to the n minus 1 times e to the negative x dx. All right. Okay, so the n comes in front. It's a constant. It's treated as a constant. It's not dependent on x, so it's a constant. All right. The next part here is the fact that the limit as t approaches infinity now becomes t to the n minus t to the n e to negative t. I've put the limits of integration. And I've noticed that this integral right here is a definition of the gamma function, gamma of n, integral x to the n minus 1 e to the negative x. So I can replace with gamma of n. Now, why did I cross out this? That's what I want to know from the chat. If anyone knows in the chat why I'm crossing out by minus t to the n e to the negative t, can someone please tell me in the chat what is going on? Okay. So what's going on here? Okay, let's look back. Let's look back here. Just give me a moment on the desktop. Does anyone know what is going on? Let me see. So why am I having a minus t to the n e to the negative t there? Okay, so nobody knows yet. All right, so no guesses? No one knows what's going on? Okay, we might need to go back to the whiteboard and help you guys out. Just give me a sec here. And we'll go to the whiteboard. Okay, well, I crossed out the minus t to the n times e to the negative t. And the reason why I did that is because it's 0. How do I know that? Well, first off, we are evaluating e to the negative t, right? So this is minus t to the n e to the negative t, okay? I'm not going to cross it out right away. Maybe I should go a little slower, okay, for those of you who don't know. All right, so minus, just give me a sec, just to write some stuff down. So initially this would have been minus t to the n, yeah, minus t to the n e to the negative t. It's t to the n e to the negative t. because I put in the limits of integration. This is the fundamental theorem calculus part 2. F of b, so you take the upper limit, this is my b. I put it in everywhere my x's are. So x becomes replaced with t, x and t, right? Minus f of a. So this would have been minus 0 times e to the 0, 0 times anything 0. So I'm just left with this. Now that I have everything in terms of t, if I evaluate, I can use my limit now. Limit as t approaches infinity. So as my t goes to infinity, my e to the negative t goes to e to the negative infinity before this guy does, and my t going to infinity. So I want to look at what happens as e to the negative infinity is happening. Like, what's happening to that? Well, this is why I like to use this unconventional approach that most math instructors don't use, and that's drawing diagrams, okay? So, and because it will tell us what it is, it's going to tell us the answer if you know how to plot e to the negative x, or e to the negative t in this case. E to the negative t, I've highlighted down here, okay? Right over here, if we zoom in, e to the negative t looks like this. So what is happening to e to the negative t? Well, you can see that it's an exponential decay, right? Okay, it's very nice. We have a neat graph here, but why do we care about it? How does it help us? Well, whether a problem is the easiest math on the planet or the most complicated, by having a graph like this, it will tell us that since we have an exponential decay, it's approaching a horizontal asymptote on the t-axis, and t is 0. So what's happening here is that this is going infinitely long. So as t is approaching infinity, right? As t is approaching infinity here, right? Because it's approaching infinity here, because this goes on forever on the tail end. E to the negative t is approaching 0, right? It's approaching 0. That's what we're saying to be linguistically correct, right? I mean, we do substitute this whole thing for being 0. This whole thing is just 0. That's why it disappears. But to be mathematically precise, we're saying it's approaching 0. Okay? So this is actually 0 here. And we're saying it's approaching 0 because of the asymptote, if that makes sense. Okay, so 0 plus n gamma of n, and then there's no t's here, and it's independent of t. So in reality, we just have n gamma of n. And we've proven that gamma of n plus 1 is equal to gamma of n. Okay? I hope that made sense. I tried to slow it down, try to interact with the audience. Don't be shy, don't be afraid, and don't be withdrawn. Try to interact with me. The best way of learning is interaction, going back and forth. Okay, I used to be like that myself. I used to be a very, you could say, a mixture of being a shy person and some other things. But it's something that can be improved upon, and it will help your learning in general, not just in math, but in anything. And also, don't get bored, because boredom is the mother of killing your learning prospects. Okay, so these things. All right. So yeah, please interact. Give me some feedback. Sometimes I might make a boo-boo here and there. I'm not perfect. So let me know. If you have any questions, let me know. If you want some more information, let me know. Any types of extra references, let me know. Like anything in the problems, in the graphs, the visuals that you need help with, just let me know. I'm here to be your mentor and your coach and your mathematical coach, if that's funny. Okay, so yes, that's what I want to point out here. All right. Okay, so we have that. Let's see what else. So we talked about that. Let's look at any suggested strategies that you guys have had in the poll. Okay, when I mean successful strategies, I'm mainly talking about anything that you would, when it comes to evaluating gamma functions in general, not just proving this one. Do you guys have any questions? Anything that you find on how to apply this, right? Actually, that's what we should be talking about. Yes, my mistake. I want to go to page 2. Okay. So a bit more on the gamma function. Okay. So the gamma function is gamma of n. So the gamma function has multiple forms. The integral that I showed you, but the gamma function itself, the most simplest way is just n minus 1 factorial for all n in the integers. Okay, that's what gamma function is. So if I had the gamma of n equaling 4, it would be 3 factorial, because n is 4, and then 4 minus 1, 3 factorial, 3 factorial, 6. Okay, so then gamma 5 would be 4 factorial, 4 factorial would have to be 24. Okay, because you're always decreasing by 1 and then multiplying it by the preceding numbers. That's what a gamma function is. Now, let's talk about some interesting aspects of the gamma function where it appears. Okay, so this gamma function, right, the gamma function, as I mentioned, I'm replacing n with z. And the reason why I'm doing that is because it is a complex, n can be replaced as a complex number. What if it doesn't have to just be a real number, integer number, whatever it is, it can also replace a complex number. Okay. So the improper integral of x to the z minus 1 times e to the negative x dx. Now this integral will converge and gives us a smooth type of extension. Okay. And you'll know here, right? Notice here that the gamma function has some additional properties that are really cool. Okay. So these are some additional properties. The recurrence property, that gamma of z plus 1 is equal to z times gamma of z. Okay. With special values. All right. So for instance, what do I mean by that? Well, special values. I probably need to walk you guys through it. So z is a complex number plus 1 is equal to z times gamma of z. Let's say if we want to find, we can find gamma of any number, any real or rational number, integer number, doesn't matter. Let me give you an example. If I wanted to calculate gamma of 1, I could have used that integral to calculate it, or I could have just used I could have used what's it called? The regular gamma function. The regular gamma function is the easiest, right? If I took gamma of 1 here, and is 1 minus 1 would have been 0 factorial, which is 1. Okay. Or I could use the recurrence property and notice that, let's see here. Yeah, I could use the recurrence property, also get it as well, right? But let's just use the regular gamma function. Gamma of n is n minus 1 all factorial. Okay. And I'm inputting right here, right? N being 1/2. Okay. However, though, if I do that, I get 1/2 minus 1, it's -1/2, and then you have a negative number of a factorial. Okay, so that's a bit problematic. So these values here, you may be asking, how are we determining the gamma of this, gamma of 1, gamma of 1/2, gamma of 3/2? Okay. Well, gamma of 1/2, okay, gamma of 1/2, all right? Well, you can do that if for A or B reason you're having problems with the gamma function. Determining a negative factorial wouldn't make sense mathematically. Okay, what we could do is replace 1/2, right, in here, right? Think of this as being n, not a complex number. We're dealing with rational numbers again. All right, so integral from 0 to 1/2, 0 to infinity, right, of x to the 1/2 minus 1 e to the negative x. Yeah, that should be a dx. Sorry, that should be a dx. I noticed a mistake here. Okay, dx, it happens. It's integrating with respect to x. That's it. So if I let 1/2 here, I get 1/2 minus 1 is -1/2. X to the -1/2 of e to the negative x. Take my word for it. You can also check resources. I'm not going to do it right now because the calculation is a little bit annoying and long, but you would get after calculating the gamma function, this guy here, okay, you will get that gamma of 1/2 is root pi. Okay, and then gamma of 3/2 would be root pi over 2. And then gamma of 5/2 would be, that's where I want you guys to figure this out. Either in the chat right now, right, if anyone is there, or if anyone's participating. There could be people who are, you know, don't want to talk in the chat. But let's see if anyone's participating or chatting. So the gamma of 5/2 and the gamma of 7/2. Okay. Anyone have any ideas in terms of how to determine the gamma of 5/2 and the gamma of 7/2? Let me go back and stop sharing. Okay, just give me a moment. Move this up. Oh, yes, we have a question. Didn't see that. Sorry, I didn't see your message right away. Yes, you're asking why the integral converges. Yes, the way to determine that, okay, if we were to go over here, let's just go back. Just give me a moment. Okay, let's go back to the moment here. Why does the integral converge? Let me just go to my share screen again. So we have an interesting, I think some interesting questions. Okay, I like good questions. It makes everybody think, and that's how we learn, right? It's by going back and forth. Okay, so let's go here. Just 1 second. Okay. All right, so this function right here, right? So the gamma function he's asking, right? This guy here. So why does it converge? Okay, so why does it converge? It converges because of the fact that we have to, if you're to determine if it converges or diverges, we have to use some integral tests, right? And you will have noticed that the integral test, right? So the integral, right? So the integral test, okay? Our function would have to be greater. Let me see again. What was my thinking process on the integral test? Yeah, because I was thinking of the integral test. Yeah, it would be the integral test, and I'm going to prove it. I can prove it using the integral test. So 1 sec. Right. So we need to look at this, right? So we would convert this guy right here. Okay. We're going to convert it to the following. Okay. We're going to convert. Actually, would it be the integral test? You have me thinking now. Yeah, you have me thinking. Let me make sure I understand your question better. Let me go back. Okay, yeah, I'll answer it here. The gamma function converges just 1 second, because the gap function converges because both because it's the real part. That's what it is. Yeah, it's the real part. Okay, because the integral can be split into parts that are both finite. Okay, because the integral can be split into two parts which are finite. Okay, so what do I mean by this? It's the fact that if you have t to the power of example t to the power of, let's say, x minus 1, okay, t to the power of x minus 1, t to the power of x minus 1 times e to the negative t, okay, as t approaches 0, right? Yeah, as t approaches 0. Okay, so as t approaches 0, the integral converges because of the exponential term, right? Yeah, the integral will converge because of the exponential term, because of the exponential term. Yeah, exponential term of e to the negative t, e to the power of negative t. Okay, e to the power of negative t decreases faster. It's going to decrease faster. Yeah, it's because it's decreasing faster. Yeah, e to the negative t is decreasing faster than the polynomial term, than the term t to the x minus 1, for instance, right? Then the term t to the power of x minus 1. Okay, I hope that answers your question. Okay, that's the reason why. Okay, it's just that the gamma function can be split up into two parts that are finite because of the product t to the x minus 1 or t to the n minus 1, doesn't matter what you call it, and then e to the negative t, right? As t approaches 0, right, this integral will converge because of the fact that the exponential e to the negative t is decreasing faster than the term of t to the x minus 1. I use x minus 1 instead of n minus 1. Okay. All right. So let's get back to the screen here. Okay. So where were we? Okay. So I don't need to show that there. And then finally, yeah, so we were talking about that. Finally, I want to talk about some real world applications of the gamma function, specifically in physics. So we have entropy. Entropy is used quite often in physics, and the gamma function is riddled all over the place. Okay, mathematics is riddled all over the place when it comes to physics. It's you can't do anything without understanding mathematics. It's so important. Mathematics is the foundation for education, practically. Okay, almost all education. So we have entropy. So specifically something called a differential entropy of the gamma distribution. Okay, and also so that's entropy is used. Entropy is used in the thermodynamics and stuff like that. In physics, I won't go into too much detail. Another thing is partitions. Partitions are partition integrals, stuff like that, in statistical mechanics and thermodynamics again. And we also have path integrals. Okay, so path integrals, I mean, what are path integrals? Actually, that's interesting. We'll talk about them later in my book. I don't know what type of sequential thing we'll do in my book that's really interesting. My book is very interesting, right? So there's a lot of really interesting topics for those of you who love to learn advanced mathematics, right? So yeah, so there's applications in path integrals. Richard Feynman, who's a theoretical physicist, came up with path integrals in something called quantum electrodynamics. I won't go into too much detail, but yeah, they're very handy, and we'll discuss that later on at some point. Not yet though. Okay, but yeah, we'll discuss that, and we'll also look. So path integrals are very interesting. The gamma function is showing up everywhere. Let me show you some of these applications. Once again, in a simulated type form here. I love simulations. Just one moment. So we're going to look at multiple simulations here. Okay, so this one, I've only made a simulation talking about micro and macroscopic physics, right? When it comes to entropy. This is the equation for entropy, okay? The sum of the exponent of negative capital E sub I, the energy relationship, that's what E sub I is, divided by Boltzmann's constant KB times the temperature. This is all raised to the power, right? Because that's E to the whole power of all of that, okay? And there's some background on this, right? We notice that the canonical partition function, okay, is fundamental for all possible microstates. Okay, just some background on this. By the Boltzmann factors, microscopic energies and stuff like that, thermodynamic quantities and so forth, okay? All right, so that's where it can be applied. More specifically to something like this, when you have a continuous partition function. Why continuous? Why is the gamma function applied in a continuous situation? Well, first off, it's an improper integral. That's what continuous is. Continuous distributions, any type of distribution or probability distribution, any type of distribution has to do with integration. Okay, so usually something like this, a continuous function. Let's see what else that I list. There's so many interesting stuff when it comes to thermodynamics that this can be applied to. And I also gave a graphical simulation of what's going on, right? So we have a probability distribution here, okay? And you can see that the probability distribution has a number of things going on. We have a 97.9% probability distribution at 0, at 0%, 10%, 10 is going to be 2%, the next one is going to be 0%, and so forth, okay? But I just wanted to give you a graphical. This is a bar graph, okay, as opposed to what I've been showing before, but hope that is interesting. I don't want to go too much into physics, but this live stream was mainly supposed to be mathematics, but I want to also show some physical implications as well, if that makes sense. Okay. Alrighty, let's go back. Let's see if anyone is on the desktop. Okay. All right, so that is practically it for my live stream. Okay, this was very cool. So again, for those of you, I hope you like and subscribe. In the description below, there's all sorts of things to my channel. Also information on my book. If you're a student who enjoys learning, advanced mathematics, right? Or you're a person who has, preferably if you have a strong background in integral calculus and linear algebra, really strong background in calculus and linear algebra, but want to learn more methods for your career down the road, because calculus is used in engineering, physics, computer science, all that stuff. This is the book for you. It will be very handy for your university studies, okay? And or if you're a student who is looking for like a serious challenge, this book is very, very challenging, right? Don't worry, I've made it in a way such that it's divided into, for those of you who just want to learn more mathematical methods, but then there's also a section for those of you who just want to tackle very challenging problems or open-ended problems. That means problems that cannot be solved at the moment. Well, we don't know what their solutions are, right? But I put them in the book for those of you who want a real challenge. And so that way you can also communicate with me, because I'd like to see see your interpretation, your guys' interpretation of how to solve these problems. I'm very interested myself. They're extremely difficult. Okay, so no one has a way to solve these integrals, but when you do, I'd like to see it. Okay, you can always message me through my YouTube channel or anything else. Okay. So as I said, there's going to be in the description link to my channel and more information. Whether you want to purchase my book, there will be a link to that as well on my channel description. If you're looking for extra tutoring when it comes to these topics or anything else, help with the university tutoring, research paper, whatever it is, I have very in-depth knowledge in mathematics. Okay, so like and subscribe. It's been a pleasure, and I can't wait to see you guys next time. Have a great weekend, great day. Bye-bye.